All right. Welcome everybody to the latest installment of the BQE. That's the Brooklyn Quant Experience, in case you were wondering. And today I'm very pleased to have Professor Claudio Tibaldi from the University of Bocconi as our featured speaker. So he's a tenured faculty member in Bocconi University, which is in Milano, and associate professor in the field of quantitative methods for economics, finance, and insurance since 2011. He holds a national qualification for full professorship since 2015. He's a fellow of IGIER and Baffy Carefin Research Centers, and has been a visiting scholar at UCLA Anderson School of Business. His research interests range in the area of derivatives, asset pricing, and portfolio management. His papers are published in leading peer-reviewed journals like Review of Financial Studies, Math Finance, JFQA, and Journal of Econometrics. And two of them have been awarded, one in September 2019 by the Canadian Derivatives Institute as Best Paper in Derivatives for the Northern Finance Association meeting, and one in January 2007 as Best Paper of the Swiss Econometrics and Finance Society meeting. He's currently serving as Managing Editor of Quantitative Finance. With that, Claudio, take it away.
Thank you very much for your kind invitation.
Okay.
Okay, so today I'm going to talk about this research project that is undergoing with Andrea Buraschi from Imperial College Business School, and I would say essentially the origin of this project was we call the paper a network paper. The project has evolved. It's now I will try to discuss a couple of important ideas. The first part, I will dedicate most of the first part to a contribution, let's say, in the area of asset pricing, without a specific reference to a given network, a given economic, well-identified economic network. Later on, I will consider the application of this theory to a network, and this network will be identified with an interbank network. Okay, so the real the key notion that I want to discuss is the notion of cascade risk. It's meant to be a new notion. We have to compare this cascade risk with, say, a risk factors. It will be related with the notion of risk factor in a general arbitrage pricing theory. As a general introduction, you recall that the risk is typically divided into, when you consider an arbitrage pricing theory or, say, a capital asset pricing model in the first stage, as in systematic versus idiosyncratic risk. So most of the literature is driven by the idea that people model systematic risk factors because those are the only ones that a rational investor should price, should attach a price if you can diversify the residual risk that is called the firm specific or idiosyncratic. Let's say that the main idea of this paper is try to challenge in an economy this separation and the assumption, which is both in the arbitrage pricing theory and in general equilibrium theory, that firm-specific or idiosyncratic shocks average out. Okay? Mm-hmm. So the main issue will be, the main questions I want to address, the same question will be addressed first in a partial equilibrium arbitrage pricing theory, and then in a Lucas economy general equilibrium, will be, can we establish some conditions to assess whether firm-specific shocks average out and do not play any role in pricing? Is this really, is the fact that these shocks do not affect an equilibrium asset prices true in general, under which conditions we can say that equilibrium asset prices and risk premia are not affected by these firm-specific shocks? And just to move quickly to essentially, I give you the main preview of these the results. We will consider let's say, an economy where you have many firms. These firms will be really stylized firms. Well, in partial equilibrium, there will be standard data generating processes for the returns. In general equilibrium, there will be Lucas trees, microscopic Lucas trees, so essentially dividend producing units. We will identify two regimes, two dynamics. In one of the two dynamics, we call subcritical dynamics. I will specify later why this name. When firm-to-firm interaction is sufficiently low, we are assuming that the network is the network created by the inter-firm interaction. If firm-to-firm interaction is below a given threshold, well, the Lucas assumption in general equilibrium, the idiosyncratic averaging out hypothesis holds. Vice versa, if the firm-to-firm interaction is sufficiently strong, this averaging out does not take place, and we will analyze the specific channel, amplification channels, and the implications. Well, this variation in the two regimes, depending on these exogenous parameters that measures the firm-to-firm interaction, has important implications for pricing. In partial, I will first discuss these implications in partial equilibrium, and later in general equilibrium, and the main outcome, the main implication is that in this region, this supercritical region where cascades can take place, I will be more precise in what I mean by cascades, these firm-specific shocks, so shocks that ideally, let's say are 1 over n, are those shocks that we assume typically can be averaged out due to some sort of law of large numbers. On the contrary, they cluster dynamically, and this creates an avalanche effect, a contagion effect, and this effect has pricing implications. Okay? So this more or less is the general picture, and later, in the second part of the talk, I will try to give you a more economic description of what is going to happen in these two distinct equilibria when we think about a network that can be properly identified from an empirical point of view, and I will focus to the systemic risk analysis, thinking about this network as the network of interaction of interbank lending. We can observe interbank lending. We can try to assess the impact of this network of interaction within the financial system into the expected returns, on the expected returns of, say, the financial institutions' stocks. Okay?
Yeah, just a quick question. Let's say there's exactly 3 firms in an economy.
Yes.
Then let's say I'm thinking there's 3 firm-to-firm interactions.
Yes.
Okay, but you're talking about a single interaction strength. So is it? Are you assuming like that there's 1 in this story of mine, or 3?
Okay. So there will be 2 parameters. Let's say I go to the equation, so we immediately specify what's the way I specify the interaction.
Okay.
I will have a well-identified parameter lambda over eta, which is common to all the firms.
Okay.
And then a network, let's call it, it will be the so-called adjacency matrix or network matrix.
Okay.
That will describe the firm-to-firm specific interaction.
Okay. So
Well, the challenge here is to be sufficiently general to capture, because as Peter was suggesting here, there is an issue, there would be an empirical issue, because we know that there are a lot of inter-firm interactions, but then measuring these interactions, the strength, the relevance, and the relative relevance is not as easy, right?
That answers my question. Thank you.
Okay. So, let me say that, as I was saying, there is a lot of literature on network economy, okay? Here, this is a super partial description of the papers that in some way are related to this paper. These are mostly papers from financial economics. There is, I would say, little, or to my understanding, 0 papers that take seriously the asset pricing implications of this network. You typically here we are talking about general equilibrium economies with production, essentially Xavier-Gabet, Alan Gay, Asimov, all these economists have tried to set up a general equilibrium economy in terms of production or in terms of interbank networks, so they have focused on the economic implications of the emergence of these networks, and which are the, let's say, the critical issues in this literature. In this literature, the critical issues are related with the trade-off you may have between diversification and the possibility to have contagion. So in practice, you try to share your risk to optimize, to reach the optimal Pareto allocation of the risk in the economy, so everybody will be better off. But in improving the risk sharing, you establish connections, and connections, by the way, drive the possibility that if somebody does not repay the debt, or somebody has a shock, is hit by a shock, this shock will be transferred through these connections, right? So the problem is that, generally speaking, in a general equilibrium economy, there is endogenous creation of a network, but this network has two countervailing effects. One positive, the possibility to share risk to the well-diversified risk. On the other, you have the possibility to being hit by a shock through one of these connections. Okay. So the main idea that is, sadly very well understood in these days, the main idea of our paper is that we want to model the propagation of the shocks in this network by using one of the models that are typically used in the analysis of virus contagion. It may be a real virus, or it may be a computer virus. We have a lot of networks. We are thinking about economic networks like the supply chain networks. We are thinking about computer networks, the web. We are thinking about networks even in terms of people connected, okay? So there are models that are typically used in biophysics, and we are going to use a stochastic model that is essentially adapted from this literature to describe the propagation of shocks in this economy. Why this is new? It's new because in a way people so far in general in finance, in financial economics, has tried to model aggregate shocks because of this Lucas assumption. So in practice, the only way an aggregate shock, especially this is well known, for example, in credit risk, so the aggregate shock will be, say, a shock to the economy and will hit uniformly through covariation. It means that essentially everybody will be affected to the same macro shock, and there will be covariation between the returns of each firm and this say general shock, a general economic shock. But what we know from the data, especially, for example, if you want to see what's going on in a credit portfolio, we know that most of the risk that is really relevant for a bank portfolio when you discuss the way this risk hits the economy is not through this common shock, through the covariation, it's through direct interaction. So if my I'm a supplier, and somebody along my supply chain is hit by a shock, I will have a direct effect. Mm-hmm. Okay, this direct effect cannot be represented by an aggregate factor. So you are forced to use a model for firm-specific shocks. But this is very far away from the way arbitrage pricing theory and valuation theories have been developed, since assuming that the economy is large enough in an arbitrage pricing theory, you typically assume that these shocks are firm-specific, and by properly selecting your portfolio, these shocks, the role of these shocks will be irrelevant for the pricing, for the market prices. Okay? So let me go quickly to the model. So the model is, I would say, it's pretty simple, it's pretty in line. So you have a purely log normal, so we are modeling here the dividends, since we are thinking about a pure endowment economy, so a Lucas economy. these cash flows, these are assumed to be the cash flows. Here we have essentially no capital structure. We are thinking simply modeling the dividend distributed to equity holders. And dividends coming from firm I will have a common shock, the regular standard Lucas one that is a log normal shock, continuously distributed, continuous path shock, and a small shock, firm specific, that it's a super simple shock because the firm essentially can be only in two states. You can think about these states like sick or healthy, or about, I will call X when this indicator HTI is 1, the shock will correspond to the firm going in distress. I remember you that a firm in distress means that the cash flows that are produced by the firm are not sufficient to repay the debt of this firm. So it's not still in default, it's, in distress you have to work to make the firm more productive and to restore normal distribution of dividends. The healing transition is the transition that takes this firm from the state 1, from distress, into A0, the H equal to 0 corresponding to the state where the firm is normally distributing dividends. Okay? So here we have, we think we have a capital N number of firms in this economy. Each one of these firms is described, it will be only different for the state of the distribution.
So is it fair to say that xi0 is bigger than xi1?
Sure, definitely. X0 is larger than X1. It's counterintuitive, but we count the distressed firms, right?
Yeah.
Because
so you should write that.
yes, you're right. You're right. So the transition from 0 to 1, it's called the distress rate, right? And the transition from 1 to 0, it's called the healing rate. For a reason I will discuss in one slide, we assume that the healing rate is uniform, constant, independent from the state of the economy. So in practice, when you go into distress, you enter in a state where essentially you are under the control of, of the authorities. You are in a situation where everything does not depend on the general state of the economy. It takes some time. You may think about this eta like the inverse of the average time that the distress resolution plan is going to take place. We think about this figure, this quantity, as state independent. On the contrary, we believe that most of the action, of the interesting action here, is about the distress transition. And you have a contribution epsilon I that is a traditional firm-specific contribution. You have a second contribution that is the critical innovation that depends on the interaction. So it depends on the direct interaction that this firm has with the other firms in the economy through this delta ij that represents in practice a number, a quantity that gives you the increase in the likelihood of a transition, of a distress transition for firm I driven by the fact that firm J is in distress. Okay? You sum over all the firms in the economy. If you have some direct connection with this firm, and this firm J is in the distress state, this will raise the possibility, the likelihood that also you undergo a distress transition.
So these H's, if we go back, are they ones and zeros, or?
Yes. This is
okay.
The state of the economy is described by this aggregate shock YT and by the H bold vector, the bold HT vector, that is a string of dummy variables.
Okay, yeah.
You will have a 1 for those firms that are in distress, you will have 0 for those firms that are normally distributing dividends.
Okay.
And the key part of my talk will be describing the evolution of HT that I will call the contagion process, right? It's a continuous, I will describe it, so
in the previous, what's the meaning of this ratio in simple terms of lambda I HT over eta?
okay, so
What is it actually telling us?
So, in practice, when you want to work with well-identified parameters. So, eta is constant, is the distress resolution, it's the inverse of the distress resolution time. It's a sort of unit of measure of time you want to measure in your economy. So, you can assume that this eta goes to 1 by rescaling all the parameters and nothing will be affected in your economy. So, essentially from now on, I will work with the stress parameters scaled by eta, and I will think about this eta like 1, like the unit of measure of time in my economy. Okay?
Yeah.
So you will see always this lambda over eta parameter, simply because that will work as the well-identified parameter. What's the role of this lambda over eta? Well, this will come at the very end of the talk. What I can anticipate is that you can think about that quantity, for example, like the average level of leverage in the economy. So the higher the leverage, we know this from corporate finance, the higher the sensitivity of one firm to an exogenous shock, because you have less less buffer of liquidity to absorb the shock. Okay. So, by the way, what's the big problem? The big problem is that typically we should think about this number as an endogenous quantity. So leverage itself evolves within a general equilibrium. But here, for the moment, we think about this quantity as an exogenous parameter. We are going to move this parameter thinking that...
Meaning lambda, right? That's what
Yes.
you Yeah.
Yes.
Okay, yeah. Okay.
Lambda over eta, yes.
All right.
Because it's the only one identified, because moving lambda and eta, yes.
Okay, that's fine.
Okay?
And the delta ij's, they're all non-negative, right?
Then they will have to be non-negative,
Yeah.
yes. And in the interbank network, you may think about delta ij like the amount of money that I lend to J,
All
right?
Okay.
So this is a simple example. You see 2, 3, 4, 5. This means that 1 will be more dependent to 5 relative to 2, in the sense that having lent more money to 5 is more dependent. Think about these firms like firms connected through a supply chain. In a supply chain, you have the two drivers. You have a productive relationship. You have a financial relationship. Here we synthesize both in a single number. Okay, so it's a very reduced form description of the network. Okay, so a little bit of why this process is interesting and slightly different from what we typically have. This is more in line with statistical mechanics of contagion, because here we have a simple Markov chain. But the number of accessible configurations here is 2 to the n, so it's exponential in the number of firms. So you have a large number of possible states, and we are thinking about n going to infinity, right? Because the economy will be large. We will have many results that hold in a large economy limit, okay? And is this realistic? Well, yes, we know. We will see that most of the results hold even for not too big economies, but the basic idea is that the results I'm going to work on are results that hold when n is very large and the limit is infinity. Okay? Then you have this big, in the state of the vector h, the evolution can be described in terms of a big 2n by 2n matrix, but this AN is the matrix that embeds the transition rates, is in fact a sparse matrix. Why? Essentially, this is a Markov process, a pure jump Markov process. You know that you can essentially describe this process in terms of simple Poisson processes, and the only transitions that have no zero transition rates are those where the two states of the economy differ for a single firm state. So in practice, the evolution of the vector h will be between two immediately consecutive states h. The difference will be only the state of one single firm. Okay, so there will be no joint transitions, because the probability, the joint probability of having at the same instant two transitions of two firms, it is, according to this formalism, is 0. Okay? So this will be, by the way, useful because it will simplify a lot.
Yeah. So there's no simultaneous
Yes.
going unhealthy.
Yes.
Or healthy. Either way.
Yes.
Right.
Yes. They can cluster, but they will be one after the other.
Right.
Okay.
Okay.
Think then, all the firms in this economy may differ only for the X, may differ for their location into the network. So the risk exposure, the traditional risk exposure for all these firms with respect to the aggregate shock, the relevant one will be the same. So essentially the beta of each of these firms, according to a standard CAPM or Lucas equilibrium, will be 1, the same. We are thinking to solve the model in the situation where we think, for example, in the case of a bank, that there is a regulatory authority that keeps low the probability, the firm-specific probability of distress transition. So in practice here, there is a rating agency, a regulatory authority that keeps low, sufficiently low the distress transition rate. We want to focus, by the way, to the solution in the case where epsilon I is very small, eventually it's going to be small as n goes to infinity, with some power as positive power, and notice this will play an important role, that if you assume that epsilon I is really 0, the configuration where all the firms are healthy is absorbing for the dynamics of this chain. Which means, you see, if H is 0 for all the firms and epsilon I is 0, when you reach the H equals 0 configuration, you're stuck. You're there, and there is no more firm-specific dynamics. Why this is interesting? It is interesting because we are modeling shocks that are firm-specific and are transitory, right? So these shocks are the typical shocks that, according to the traditional point of view, should not play any role within the general equilibrium economy. So an investor, if we forget the interaction term, these shocks should not have any price of risk, right? Because you can diversify, they are transitory, while in macroeconomics the only relevant shocks are the permanent ones, are the random walk shocks, and they are firm-specific. So apparently you can diversify these shocks, right?
Okay, so you see what I understand. So you said
Yes.
if epsilon I is 0,
Yes.
and if all of the firms are healthy,
Yes.
then they're going to stay healthy forever.
Yes.
Okay. But say all the firms are healthy, but epsilon I is not 0, then some firms can become unhealthy.
Yes.
Okay.
Yes.
Okay.
So I will solve the
Yeah.
model with epsilon I different from 0 but small.
Okay.
But the basic, it will be an important fact, that in the limit of n very large, when epsilon I has to be very small, because I put in this constraint, the Markov chain will have this absorbing state. Okay? Then let me spend 2 seconds, this is for financial economists, trying to explain. I'm doing a lot of parametric choice. I'm in practice considering a very well-educated guess on the transition rates. So my friends economists would wonder, why are you choosing completely asymmetric, or maybe you had a
Well,
question.
you just go back to the earlier slide regarding so why is that correctly that what's happening is you have this generic or systematic process which is evolving Brownian motion.
Yes.
And then so as you forward in time,
Yes.
that diffusion is occurring.
Yes.
And you have this vector, the HI, which is either 0 or 1, is
Yes.
diffusing as well.
Yes.
But there's no connection between the diffusion of
No.
that generic factor and the HI?
You're right. That's a limitation of the model. The aggregate shock and the first specific ones
Right.
here have essentially an independent dynamics. Okay.
So when let's say for a given firm I equals 1, H is 0 at
Yes.
time t,
Yes.
then it will spin off a dividend, you mean,
Yes.
right?
Yes.
Based on the evolution of that diffusion.
Yes.
But if it's
So-
1, it doesn't generate.
The basic idea is what the thing that is
Right.
called the permanent transitory decomposition in macroeconomics. So you have aggregate shocks that are permanent and hit through the Y, and you have the XI, that is the transitory dynamics driven by the balance sheet of the firm.
What are you calling the white?
Can you back one slide, because he's actually talking about the previous slide, this one.
Yeah.
Yeah, so the dividends are actually not zero in the distress state, they're XI1, whatever that is.
You can
Yeah.
put you
Okay.
can put
Yeah.
zero, but they will not be zero, generally speaking.
Right.
Yes. You can solve them
So
also with
basically,
zero.
you should think of it as high and low dividends. So
Okay,
XI0 is
yeah.
high dividends,
Right.
XI1 is low dividends.
Yes.
I mean,
No, but it can be zero.
it
won't
can
a
be
problem.
zero, but it can be more general. So let's say in general, there's dividends in both states.
Right.
And, but XI0 is bigger than XI1, so
Yes.
So, and, well, so the more firms that are unhealthy, I guess the thinking is the lower is the aggregate dividend.
Yes.
Yeah. Right.
Yes. So in equilibrium, you will have a lower dividend. This will hit consumption, and consumption will feed into the valuation.
And the next to last line,
Yes.
that's the evolution of the HI vector,
Yes.
right? So the H of t plus delta t
Yes.
will come from H of t,
Yes.
the transition of each of the HIs,
Yes.
through the matrix delta.
Through this capital matrix A, that is the transition rate matrix, whose elements are set by this lambda and eta of H, right? So once you specify the distress rates and the
Cure rate.
and the healing rates for each firm, that will depend on the full vector. So the key characteristic you see is that lambda I depends on the bold age. So the possibility for you to go in distress depends on any other firms you are connected with, right? So it's the interaction that is doing the action in this movie, right? You know, here there are two big assumptions. One is asymmetry, the fact that we are considering interaction for distress transitions, we are not considering interaction for healing transitions. By the way, we could do something, but this is driven by empirical evidence. We know that in practice, people price, the pricing effect is far stronger when you are in the good state and you go in the distressed state than vice versa. Okay, so this is there is a lot of literature. I want to stress this is very important. This is why I decided to give this talk here with Peter in the audience, because equity, when you want to price, here we are thinking about pricing the stocks directly. This is the typical exercise, but you may think also of pricing a cross-section of equity options, or even jointly the shares of equity and the options written on these shares. And what you learn when you look at jointly, if you try to create portfolios of options and underlying stocks, you learn that most of the action is not captured by movement in the beta and the risk exposures according to the standard capital asset pricing or consumption capital asset pricing, because most of the risk is hidden into these idiosyncratic shocks.
Yeah.
So there is a recent evidence, I think that the most convincing paper is this paper by Lin and Todorov that is very recent, that the relevant shocks, and this goes back to your question, that move the cross-section of equity options have zero beta. It means that...
So I just have to say, Todorov is one of our speakers this semester.
Great. So maybe he's going, I hope he's going to give... He's doing econometrics, convincing econometrics, high-frequency econometrics, showing that the beta, that these are market-neutral shocks. So in practice, the beta of these shocks is irrelevant, which in a way supports the idea that we can look at the H and we can look at the I in an isolated way, okay? Which is in a way the more challenging, going back to the credit risk analysis, we know that, you can use Cox processes or this conditional factor modeling, but most of the action in the price of the portfolios of the banks will be lost, okay? So, and then last but not least, going back to our defaulted or distressed banks dynamics, what we want from a dynamic point of view represent is the clustering. So what we observe is that the models where you run distressed states, or you run factors diffusion-based factors struggle in representing the clustering of the crisis. Okay? So, the proposal is, I think now it's pretty clear, it's okay. Now we try to use this a string of dummy variables to represent this contagion process, and we want to represent cascade risk for this process. So the idea of cascade risk is the idea of clustering of a crisis for this contagion process H of t, right? So the key definition is the definition of cascade. What is a cascade in this economy? So in this economy we define, so think it's easier if you think about the economy with the absorbing state. Then the challenge is to generalize. If you have an absorbing state, it's super easy to understand what's going to be the notion of a cascade risk. Essentially, assume you flip a set S of firms, so you send in distress for some exogenous reason S firms, you can measure the time required in the economy to go back to the normal distribution, the H equals 0 state, and the length of that perturbation, of that fluctuation, will be a good representation of the severity of your crisis.
Okay.
Okay? Now, the idea is that you want to have something, a definition that is robust with respect to the possibility to have firm-specific shocks. Okay? And so you define a mean time that it takes your economy to go back to the steady state. Once that you perturb it, you go out from this steady state. It's a sort of extension of this absorbing time. Here you are not going back to a specific configuration. You want to go back to some configuration with some probability, that is the probability that that configuration occurs in the steady state. Okay? Luckily, this quantity for an ergodic, for a recurrent chain, is well defined. It's called the Kemeny time. The Kemeny time of the chain, it's well defined. It has a lot of interesting properties. So we think about the epsilon I larger than 0, so our chain will be recurrent ergodic. And you can measure this time, you can define this time in this way. It will be essentially, once you perturb, you start from an economy where only the S set of firms is in distress, and Ts of H will be the time required to hit H. You weight each configuration H by the probability of being in H in the steady state. I recall you that the steady state vector is one of the eigenvectors, of the principal eigenvectors of the rate matrix A, the one corresponding to the eigenvalue 0. So in practice you have this eigenvector, you compute this mean, this quantity is called the Kemeny time. The Kemeny time has interesting properties. First of all, it does not depend on x. So in practice you have a measure of time that does not depend on your exogenous fluctuation. It's a spectral invariant. It means that it depends only on the spectral properties of the transition rate matrix. And this is why we choose this quantity, because we want to have a quantity that is invariant with respect to say, the representation of the dynamics.
So
Okay?
the fact that, so the mean time doesn't depend on S, but the actual return time does? Is that what happens? Or?
Well, it's the expectation doesn't. By the way, along each realization you will have a different time, yes. But we want to have a measure that does not depend on the original perturbation. It has to be invariant with respect to the exogenous.
But I thought, like the whole point was that, say, the more you perturb, then the longer it takes to come back. And so
That's
you
a
can use
great question. So the problem is exactly this one. You don't, here the idea is that we want to have at first specific level, we want to control the size of the noise, because we know that arbitrage pricing will hold when the noise is going, is going to 0. You can diversify it. So we want to stay close enough to a situation where this noise is small. But on the other hand, we want to have a representation of the endogenous channel. So we want to know, given a state of the economy, endogenously, how that economy is prone to being hit by a severe crisis. right? So in other terms, if S is, if I assume that all the firms in the economy are hit by this shock, well, it's obvious that the time it will take to go back to the healthy state will be longer compared to a situation where S is a small cluster. But what I want to model is a situation where I flip a single firm, and this may generate a cascade that is large and gives rise to an aggregate effect. Okay? So I want to represent the endogeneity of the effect. Okay? So I choose this T for that reason. Okay? Because I want to have a measure of the exposure to a cascade of and then what I define as a cascade is a situation where depending on the exogenous parameters, essentially to the lambda over eta and to the delta, this time is exponential in the number of firms. So essentially, if when it is exponential, this means that you have no way to remove the impact of this shock, even if you could start from a single flip. Okay. So if this is not this is borrowed from this contagion literature, the fact that you force this n. In the original traditional contagion literature, you can even take n going to infinity, and that would simplify your treatment. But the problem is that we want to have something we can test on a real economy, and so we take this definition. Okay? We will say that in a state of economy there are cascades if the time of return to the steady state is longer than a quantity that is exponential in the number of firms in the economy. Okay? And this will be an endogenous characteristics of the state of the economy. It will not depend on the severity of the perturbation that hits that we will think to be very small. In the limit later on I will take it going to zero. Okay? So in practice, in this economy, I will say that there are cascades if a single flip may drive a crisis in the full economy. Think about lambda over eta like the leverage. Moving lambda over eta, I will pass from a situation where exogenous shocks average out quickly to a situation where even a single firm may drive an aggregate crisis. And the key theorem, well, the first key theorem, that is a theorem that in practice extends known results in the contagion literature, is that the transition between the situation where lambda over eta is below the does not generate cascades to the situation where there are cascades, it's discontinuous. There is a threshold, the value of lambda over eta. Below that value, the probability of having cascades is zero. Above that value...
So I understood the definition of cascade to involve n going to infinity. Is that wrong?
No. It's not for n going to infinity.
Okay,
this is the
I'm not
traditional...
understanding cascade. So n
You must have n zero, and
okay.
then, the traditional... This is a key point, in a traditional model, you would take n going to infinity.
Yeah.
We keep n finite. We
Okay.
simply ask that Tg is larger than a to the c to the n. And we will say that in an economy sufficiently large, it means I take n0. If n is larger than n0, I will say that there is a cascade if Tg is larger than the exponential of c to the n.
Okay.
Okay?
Fine.
Yes?
I'm sorry, Peter. Yeah.
No, that capital N is finite there. In
Yes.
the theorem on the next page, right? On the
Yes.
this page,
Yes.
this theorem, n here is finite, right? It's,
Yes.
Okay.
Yes.
Okay, fine.
So everything is known, I'm taking the result from n going to infinity, but this result called for n finite and epsilon I different from zero. This is the mathematical challenge.
Yeah. Agreed. Okay, good.
Prior slides, sir.
Yes.
So I understand what TSH is, basically the mean time it will take you to end up in state H when you're starting in state
S,
right?
yes.
So what is the economic content of this weighted average of the mean? In other words, the definite TG, it's the weighted average of the mean times.
Yes.
Right? By these probabilities pi A, right? What is
Yes.
the economic content of that? I know it's linked to the cascade of it, but what does it mean economically? You're averaging these mean times you're averaging the time to return to state H
So-
over all states H.
So, it's a super good question. We are struggling to give an economic meaning. As I was trying to suggest, this is a really intrinsic property of the dynamics. The basic idea here is that you want to reach, you want to wait more the time if this configuration is going to happen more frequently, right? And the key property is that everything does not depend on S. This is like some second of magics, but this has to do with the mean time it takes. It's the recurrence, the ergodicity of the chain that makes this possible. Okay, I will go. These are the technical details that are really, we are this definition using this many time is new. This is due to the fact that otherwise people could say that all the results depend on the details of your selection of the transition rates. While by selecting an ergodic state, an ergodic chain, so a chain that has a generic epsilon I different from 0, and everything in line of principle goes into a well-defined steady state, even showing that in this very general situation, you may, you may find cascades, this clustering of events. This sounds, from an economic point of view, super important because it's telling you that cascades are generic. You have to take into account the possibility of have cascades in a very general situation. It's not something specific to the parameterization of your model. Okay, just to be precise, when you set epsilon I to 0, the supercritical state is what is called the situation where the contagion is endemic. It means that you have a probability, a finite probability to reach to get sick, even if you are completely healthy, independently from your personal health. Okay? So it's a situation where the probability, you have a finite probability of being hit by the contagion, irrespectively of your personal state. Okay? You can do whatever you want on your balance sheet, but this will not be enough for you to stay safe from the crisis. Okay?
Yeah. So can we go back one slide?
Yes.
In the subcritical case,
Yes.
what does it mean? Like, why is it that you never get a cascade?
Essentially you can prove that in a logarithmically short time, you go back to the steady state, to the empty state.
Okay.
Okay.
So there's no existence of the C or N0 on the previous page.
Yes.
Okay.
The key fact is that you must find that C and it must be exponential because essentially you can send epsilon to 0 in terms of a positive power n to the minus rho, but there will not be enough in reducing this TA. There is an interesting result that shows that this TA has also an additional significance compared to the one of the TA. It's essentially it's giving you the sensitivity of your state to a small perturbation from outside. Okay.
Yeah.
So if it is exponential in n, this means that in practice it will be infinite in any realistic situation within this economy.
Yeah.
Okay.
So saying the probability of a cascade is 0 is another way of saying the return time is sufficiently short.
Yes.
Yeah,
Yes.
okay,
Yes.
okay.
Essentially, you may have perturbations, but this will be local crisis. It won't be an epidemic state that has aggregate implications.
Okay.
And by the way, the guess is that we expect only aggregate cascades to hit the rational investor, right?
Okay.
So in practice, if you want to have a simple intuition, think as a cascade like a branching tree. In practice, there will be a separation. That separation will correspond to the situation where if there is one agent that is going to distress, one firm going to distress, this will propagate at least to one additional directly connected firm that is stressed. If this number, that is called also the reproduction number, is larger than 1, you will be in the supercritical. If this reproduction number is below that threshold, it will not, essentially will decay exponentially quickly, right?
Okay.
Now I go to, the main course, that is, I want to see how this cascade effect It's, how much time do I have?
10 minutes.
Okay, perfect. So the time to represent the arbitrage pricing theory result. So, no, but it's enough.
In the subcritical case here.
In practice, my exercise is the following. I replace the traditional noise in an arbitrage pricing theory with a noise that is in practice this contagion process. So I think about the traditional capital asset pricing model. I have an aggregate shock, that is the market shock. I have an idiosyncratic shock. How do I model the idiosyncratic shock? Well, each time there is a distress, the price jumps down. Each time there is a healing, the price jumps up. And you know, I choose a very special parameterization to have a very easy closed form solution. And the parameterization will be, you see, 1/n, so it will be spreading uniformly across all the firms. I sum, in this case, I can, you know, all the firms are equal, so I can sum and have two sources of I can represent the full contagion process in terms of two Poisson processes, the total number of distress transitions, the total number of healing transitions. I take a well-diversified portfolio, which means I take the portfolio where each firm stock return as weight 1/n, and this is the typical situation where you would expect that this quantity averages out when n goes to infinity, right? So this is the 1/n, and we want to verify that, as expected, when lambda over eta is larger than 1, this quantity doesn't go to 0.
Right.
Okay. So here we can represent the dynamics in this way. You see, essentially, we are renormalizing by their transition rate the Poisson processes. We have the evolution of the total number of distressed firms, this I stands for infected, evolves according, this is a birth and death process, it's a very traditional process. When n goes to infinity, by the strong law of large numbers applied to the process, this y plus and y, so in practice these quantities converge to 1. And surprise, you are left with a situation where your dynamics becomes, in the limit of n going to infinity, goes to a deterministic limit. Okay? So in the limit of n very large, the probability to be close, your solution, your stochastic solution to be close to this deterministic solution is essentially 1. Okay? It's very large. So to be precise, this is the estimate. The limit for n going to infinity of the probability to have a difference larger than epsilon goes to 0 with n going to infinity. What's going on here? So take the long-term state that is the steady state. You find that the steady state is characterized by two solutions. One is, as you would expect, 0 infected, so the distress averages out, or a situation where I star is larger than 0 and is 1 over minus eta over lambda. Okay? So if you are in the subcritical, so 1 in this case is the critical point. So if you are in the subcritical state, that is this limit is 0.
Okay.
So no pricing impact. But if you go into the supercritical state, I star equal to 0 goes to 0. It's unstable. So even an infinitesimal perturbation out of I star from 0 will drive you out, and it will make you converge as time goes to infinity to the different solution that is an I star that is different from 0. But I star, a level of infected, a finite fraction of infected firms implies a finite contribution to your expected return. Okay? So in other terms, this relationship, that would be the conventional.
So you can't diversify.
You can diversify.
You cannot
because,
diversify. And
yes.
what
And-
remains is say, is positive amount of variance from this portfolio that's equally weighted with an infinite number of firms in it?
Yes.
Right, okay.
Yes.
Okay.
So the basic idea is that even in such a simple setup like a CAPM, if you have a contribution that may drive an interaction that may drive this cascade effect,
Yeah.
this generates a priced alpha, so a priced anomaly, right?
Right.
And this quantity will depend on the price appreciation, the price depreciation, by the amount of, how far you are into the supercritical region, and this H is simply due to the fact that we are taking a return over a finite period of time.
Yeah.
H.
So like we call it idiosyncratic, but all these firms interact with each other. So
Yes.
like, why,
So what's the problem?
Yeah,
What's the problem
meaning of
here?
idiosyncratic?
It's
Okay.
definitely
Yeah.
not systematic. What we can say is we call it now cascade risk, right?
Okay.
Because on one side it's not systematic. There is no common shock here.
Yeah, like when I invest in exactly one firm, but
Yes.
they interact with everybody else.
So
I mean,
the,
effect investing
the
in all
critical
firms.
condition
Yeah.
is that even flipping one single, so sending to distress one firm,
Uh-huh.
all the firms are under regulation, so their firm specific credit risk is low, still you may have an aggregate effect, right?
Yeah.
So now the key question mark is, okay, you showed us that this happens when n goes to infinity. What's going on when n goes to is finite? Okay, so now the tricky part, but then I will skip quickly because you are not really, if you are not, this is, let's say, further. It's how can I specify a measure? Because now I reproduce this result in a super simple CAPM, right? But assume I go in a state contingent model with a lot of contingency and so on. Which is the pricing measure I should use? Because here everything is based on a CAPM setup where we assume that the risk can be well diversified.
Mm-hmm.
So the basic idea is that you have to go to a construction of what is called a quasi-steady state. So if you want to know what's the pricing measure in this economy, you have essentially to think about the formalism of Hansen and Scheinman. That is a formalism where essentially you model the evolution of cash flow risk in terms of a Markov process. This Markov process is essentially the process coming from your contagion process, condition not reaching the zero state, okay? And there is a full construction framework that gives you finally the possibility to compute a pricing measure that we should call the long-term risk measure that is different from the one you would expect based on a simple rule. Okay, so what's going on now? This is the part I wanted to show you. Now, you can complicate everything as much as you want, but the results are not going to change. First of all, how do you want to represent firms that have different exposure? Well, you take the principal components of the network matrix. You have this measure that is like the centrality, but here is for directed networks. You have hub and authorities. You may measure the systemicness of each firm, the vulnerability of each firm. In terms of these two quantities, you can qualify how much each firm is exposed to this cascade risk. Then we move into general equilibrium, so we want to see not only the quantity of risk, we want to see also the price of risk, how it moves when you consider the possibility to have this cascade risk. And essentially what you can see is that each, using this parameterization, each chain corresponds to a chain. You can represent each chain like a star network, where essentially you have a central representative level of distress that measures the level of aggregate probability of being hit by a cascade, and then an indicator near that measures the exposure. And given, now we take n going to infinity, we can have a fully analytically characterized solution where you have an exact expression in terms of the characteristics of the network of your critical level of leverage of lambda over eta, you can characterize the probability of exposure of each firm to this cascade. In the end, going to infinity limit, you can have analytical results. Okay? And so what's left is, let's see whether this valuation, these cascades in general equilibrium modify the valuation by the agent. And as expected, we have two additional contributions. These would be the standard Lucas premium. So here I'm looking at the price of risk in an economy that is super critical, where I want to assess which is the excess risk premium that I have to pay if I want that somebody buys my shares, right? So there are two additional terms that, by the way, depend on the exposure of firms to this cascade risk. What is very important is that the traditional notion of risk-return trade-off here breaks down. So you have, and this we know is consistent with what we see in the data. There is something that is called the idiosyncratic risk puzzle. You see that firms that are less exposed to idiosyncratic risk pay a higher return. This is something you can reproduce because you understand that the qualitative nature of this risk is different, right? Yeah. So in practice, the risk-return trade-off concerns systematic risk. Vice versa, here you have a non-systematic component. Going to pictures, this is for macros. So what you can do with this type of representation? Well, you can consider how stable is your economy in relation to the geometry of the network. If you want to have a centralized versus a complete network, you can compute, for example, you can verify that if you are in the supercritical threshold, diversification breaks down and the basis spread, an interbank basis spread focusing on banks, opens. You can characterize the risk premium. You see that two banks, here we are in the interbank framework, two banks that had the same pricing in the subcritical state have a spread. This spread relates with their exposure to these shocks when you are in the supercritical spreads. Now, here we are moving the geometry of the network, so we are thinking about more concentrated, less concentrated networks. So we are varying the pricing in relation to the geometry of the network. What is interesting is now, it would be interesting, but this is definitely for the next seminar, it's about the endogeneity. So think about a real network. The real network is endogenous. Where would you put? So lambda over eta will move endogenously. Where would you locate, most likely, the lambda over eta? Most likely, if you push for diversification, you will rise the lambda over eta. You will rise, but not too much. It will be immediately, the optimal point will be immediately below the critical point. So a small shock may drive you up. This may generate endogenous crisis. And what is really interesting is that the system will be close to a critical boundary. It means that the situation will be a situation where an arbitrarily small shock may drive you into a severe crisis. You can do an example. You have country A, country B. Think about these as banks. Think about the country B. You are close to the critical boundary. Assume that country B is willing to push risk sharing, to push push growth. So they reduce the regulation. So they allow to local banks to rise the amount of credit they issue. So what is going to happen is that if the amount of interaction among these two rises enough, a small shock will drive the system into this supercritical state. What is going to happen is that even a local shock may hit the global economy. Think about this like the international connections, may drive a crisis over worldwide. Okay, so going to the general equilibrium, what you would expect? You would expect that the risk you are pricing is the left skewness of consumption, and this is the case. You see, this is the evidence of what is going to happen in this crisis. You see that what is going to change heavily is the skewness of the consumption distribution,
and here you have what happens in terms of the returns, the cross-sectional distribution. And that's all, you know. You see that in this supercritical phase, you have a cross-sectional distribution of risk premium depending on the characteristics of the firm, which is something you couldn't have in a standard arbitrage pricing theory. And I think it's a good point to stop.
Okay, all right, thank you. So I guess like you could use the model to predict definitely whether or not a cascade occurs, right? And also, in theory, to price all assets. And the way, let's say, pricing occurs is that if the situation is such that you cannot fully diversify, even though, like, you have an equal weighted portfolio in an infinite number of firms, but nonetheless,
Yes.
the variance does not go to zero. Then there's, let's say, there's what, higher expected return than in the opposite case when you can diversify. Is that fair?
Yes, you're right.
Yeah.
Sure. Yes.
Okay.
It would be, so as far as you have a distress risk premium, there will rise the key point is that there is the exposure effect. So the more you are exposed to this cascade risk, the higher your additional risk premium you want. Because you know, you are paying an insurance with respect to being hit by a cascade. But what is key is that it's an unpredictable HI of T. So in practice, where is the state where you are most exposed to this risk? It's the state where you believe you are in a good state because the aggregate economy is in a good state, but still, you know, there is a lot of, you are very close to the critical point, so a lot of firms are healthy, so you believe, okay, I'm in the upside of the cycle, but then a small kick will drive you into the supercritical, and this will generate a big jump.
Nowadays, that's pretty much what everybody's saying, right?
That's the you're at the edge. You're at the edge.
Tomorrow,
Right?
we're going to be talking about that.
So this is more or less why this is it's no linear the impact, because the impact will be more severe when apparently the economy is in the best state. And you know, this is just from a mathematical point of view. If you try to write down the stochastic discount factor to move from the pricing measure to the P measure, that why we call it's not possible to reduce this economy to a standard economy with multiple factors. Because here it's the number of sources of risk that is stochastic. Because each firm can contribute also to propagating risk. So the general expression of the stochastic discount factor is related with this quasi-stationary measure, and it's it cannot be reduced in any way to a factor model, a traditional factor model.
Like, to me, the big drawback of a classical factor model is that the number of factors is fixed.
You told me, yes. That's
you fixed that. So,
so
huge.
here it's even stochastic, right? And this is what creates the cascade. The fact that sometimes, the number of small sources of risk is going to decrease. Sometimes even a small shock may drive a huge and exponential rise in the number of firms that drive and suffer risk. So it's like the snowpack, the avalanche formation on the snowpack.
Yeah, so let's say there's an infinite number of firms.
Yes.
And then you're thinking the number of factors at a point in time is the number of firms that are, quote, unhealthy at that time?
Yes.
Okay, that's nice. All right.
Yes.
Okay.
Okay.
All right, thank you very much. Yeah.